Okay, thank you. And thank you to David and colleagues for organizing this workshop. I'm Yashas Annadani, and today I would be speaking about variational causal networks, approximate Bayesian inference over causal structures. So this is a joint work with my colleagues from ETH Zurich, Mila, and MPI. So before going into the technical details of what we have done, I would like to briefly motivate the problem we are trying to solve and then go into the technical details. So in this work, we are in general interested in learning causal models. This is typically called as causal discovery, and it is usually done with either observational data and/or experimental data by making set of assumptions about the data generative process. Ideally, we would like to make as few assumptions about the causal model as possible before doing interventions. Ideally, we would like to plan them such that we would be doing only a few of them. So in this work, we would restrict our attention to linear structural causal models. And to give you a more concrete idea about them, so we are dealing with structural equations wherein each variable xi is a function of its parents in the causal graph and a noise variable. We assume that these variables are continuous and the function fi is linear parametric with additive noise. So in that case, each variable is basically a linear function of its parents in the causal graph and an additive noise variable. And we assume that there are no hidden confounders or no latent variables. And this problem of causal discovery is quite hard because the space of graphs, which is discrete in nature, grows super exponentially with the number of nodes. And searching over the space of DAGS is quite hard. As you can see in this table, as the number of nodes grow, the number of DAGs as well as the number of graphs grows exponentially. And even if you could somehow restrict the space of DAGs where you would like to search, the causal graph may not be identifiable. So typically, when using only observational data, the key element is identifiability, which is the result that we cannot recover the causal graph from just observational data, even with infinite number of samples. So a lot of assumptions are typically made to make the causal graph identifiable from observational data. On the other hand, we could do interventions or experiments which improve identifiability, but they're hard to do in practice. So on one hand, we can make more assumptions about the structural causal model and make the causal graph identifiable from observational data. However, these assumptions may not be satisfied as part of the data generating process. On the other hand, we can make interventions, but they're very hard or sometimes even impossible. Which basically brings me to the central question we would like to address in this work, which is, can we get good causal models without making a lot of assumptions while still doing fewer experiments? And one way to do this is to do Bayesian learning of causal graphs. In order to do very few experiments, we need to plan the interventions and then select the most informative ones. And one way to do this experimental design is to get uncertainty quantification of causal structures and then use this uncertainty quantification for experimental design, like I mentioned. And this requires Bayesian learning of causal graphs. To put it more concretely, what we have is we assume a prior over the causal structures with given by P of G, and given observational data D, we are interested in the Bayesian posterior. So the real difficulty of this problem comes in evaluating the evidence. Even though you could solve this analytical problem of marginalizing the theta by assuming a conjugate prior over the parameters, like I mentioned, there are super exponential number of graph configurations which needs to be summed over. And in addition, In the non-identifiable case, this posterior is multimodal in the sense that the graphs inside the Markov equivalent class, which is part of this non-identifiable set of graphs, have high probability under the posterior. So in addition to this multimodal nature, apart from the fact that we need to be able to model this multimodal nature, we need to be able to search over the combinatorial number of DAG structures and have to keep a distribution over the space. We need to be able to sample from this distribution if you would like to compute some quantities corresponding to this distribution. And in this work, we would like to ideally achieve this as a smooth optimization technique so that we can use learning-based techniques. And in general, Bayesian learning of causal graphs is a harder problem than just causal discovery. So before I go into the main contribution of this work, I would like to highlight the two main techniques which have been used for Bayesian learning of causal graphs. And that is to use a conjugate prior over the parameters theta and then performing MCMC. And the other technique is DAG bootstrap. So in this technique of conjugate prior, we assume a conjugate prior over the parameters theta, and this helps us to obtain an unnormalized posterior over the graph structures. And then we can sample from this unnormalized posterior using MCMC techniques. But the limitation is that we need some graph search heuristics to explore the space of DAGs. And in general, they show very slow mixing and convergence. So the other technique is DAG bootstrap, where it's not a Bayesian method, but it helps us to obtain some sort of uncertainty estimates by bootstrapping samples from our data and then obtaining an estimate of the causal graph using some of the causal discovery algorithms for each bootstrap set. And then using this estimate, we can obtain an empirical estimate of the posterior by based on the normalized frequency count. And in general, it does not have full support over the space of all DAGs. And this can be limiting in some scenarios, for example, in the case of experimental design. So in order to circumvent these problems, we propose variational causal networks, wherein we perform variational inference over causal structures. So we assume that we have a variational posterior Q phi of G with a parametric variational family. And the elbow, the evidence lower bound for this variational inference problem looks something as follows, wherein we have these two terms. One is the likelihood term and the regularizer given by the scale term. So this elbow is still intractable if this variational posterior is approximated naively. So the real challenge of this problem lies in how do we actually parameterize this variational approximation so that we can optimize this elbow. So let's try to look at what this variational approximation needs to contain. So the first constraint is that it needs to have support over the space of DAGs. And ideally, we would like to have some sort of sparsity encoded. And the parameters of this distribution should not grow super exponentially with the number of nodes. And like I mentioned, since we are dealing with the non-identifiable case, we need to be able to model multimodal discrete distributions. So let's first try to look at how do we actually try to enforce the first two constraints. Instead of directly parameterizing these two constraints in the variational approximation, since we have a regularizer in terms of the KL, we enforce these two constraints through the prior P of G, and then hope that the regularizer helps us to obtain an approximation which also contains these constraints. So put it in a bit more detail. The prior should be such that only DAGs should have non-zero probability. And ideally, this corresponds to a uniform distribution over DAGs. And in this work, we would like to have a smooth characterization of DAGs if you would like to use gradient descent techniques. And in order to have this smooth characterization, We used the result of the no-tiers approach, which is a result from 2018, which says that the level sets of the matrix exponential of the graph adjacency matrix characterizes DAGs. That is, if an adjacency matrix A of G corresponding to a graph G is given, it was shown that it is a DAG if and only if this constraint is satisfied. So what this does is it turns a combinatorial problem into a continuous optimization technique in the case of causal discovery, but we still have to address how we can use this for our variational inference problem. So let's try to look at the prior P of G again, and to recap, it should be such that the DAG should have non-zero probability and the edges are sparse. What we do is we define this Gibbs distribution, which contains two terms corresponding to these two constraints. So here, this L1 penalty is corresponding to the sparsity, and here f of G is basically the no-tiers constraint, which I just discussed. So lambda t and lambda s are hyperparameters, and ideally, if you would like to have a uniform distribution, then lambda t tends to infinity. So it remains to be seen how we can enforce the other two constraints, and in order to do that, we basically look at how we can actually efficiently parameterize the variation approximation. So I'll present three different possibilities and then discuss the merits and demerits. The first possible way we could parameterize this variational approximation is to make this as a categorical distribution over all the graph configurations. But then we have not achieved anything because we still have super exponential number of parameters for this distribution, and the elbow is still interactive. So the other way is to define distribution over adjacency matrices. And each entry of this adjacency matrix corresponds to the presence or absence of an edge. And we can model this as an independent Bernoulli random variable. So what this does is it reduces the number of parameters to d square, but this cannot model multimodal distributions because a factorized distribution is a unimodal distribution. So we need the higher order dependencies if you would like to model this multimodal distribution. Which basically brings me to the main contribution of this work, which is to model distribution over adjacency matrices using an autoregressive distribution. So now, instead of having these Bernoulli parameters in the adjacency matrix, instead of making them independent, we introduce dependencies among these entries using an LSTM. We could also use other autoregressive models, but in this work, we use an LSTM. And this basically helps us to model multimodal distributions. And as we shall see in the results, this is actually pretty effective. And in order to obtain the gradients, we use the scope function estimator. And to obtain this marginal likelihood where we marginalize the parameters theta, we use what is called as a BG score, wherein you can obtain closed form solution of the marginal likelihood based using a Gaussian-Wishart prior. And what we have achieved with all of this is that now we don't have any slow mixing issues, and we do not require any DAG search heuristics. And it has full support over the space of all the DAGs, at least that is the hope. And we can train it using gradient descent techniques and learning-based methods. So I would like to briefly go through the results, and we performed some experiments on the synthetic data, wherein the graph is generated from an Erdos-Renyi graph model. And the causal graph is not identifiable in this setting, which is the setting which we are interested in. So for very small graphs where the number of nodes is less than or equal to 4, we can actually compute, we can basically enumerate all the graphs and compute the true posterior. And what I've plotted here is basically the Hellinger distance between the model which we have learned and the true posterior. And as you can see, the autoregressive distribution usually performs better than the factorized distribution. And this is mainly because of the multimodal nature of the posterior. And in order to make a quantitative comparison in higher dimension, we compute what is called as expected structural Hamming distance, which is basically computing structural Hamming distance for graphs which have been sampled from the model. And here lower is better. And as you can see, the proposed autoregressive distribution of VCN achieves better performance than the MCMC and the bootstrap techniques, as well as the factorized distribution. So in summary, what we do is we perform variation inference over causal structures to obtain uncertainty estimates. And the crucial part is to model the distribution over adjacency matrices with an autoregressive distribution. And like I mentioned, we could use these uncertainty estimates for experimental design, for example. And if you'd like to check out the code, or if you'd like to check out the paper, I have attached my GitHub page, which has all the relevant links. And thank you for your attention. If you have any questions or if you'd like to discuss, I'm more than happy to do so right now.
Thank you. Are there any questions for Annadani? Can I throw a quick one in before there's any others? Is you say this, you're using an autoregressive model, but like, and you're given like a nice diagram of like, you don't want two-way arrows. How are they actually prevented? Is it like, do they have to be learned to be prevented, or is there some way you can build that you know that's not okay?
You mean the multimodal nature of the true posterior?
I mean that you know some of the G's are forbidden, like there's constraints of like you've got the red X in the bottom saying you can't.
Yeah. So
how do you it seems very complicated to remove that from the support of a distribution.
Yeah, you are pretty much right. So the way we would like to remove the graphs with cycles is by enforcing this DAG constraint, which I just discussed here. So ideally, we have this algebraic result where it shows, where they have shown that the level sets of this matrix exponential of graph adjacency matrix characterizes DAGs. What we do in this work is we come up with a Gibbs distribution which encodes this constraint, wherein it ideally penalizes all the graphs with cycles.
So, but they still have support, but they're not so much support.
So ideally, so the support is actually is traded off with this hyperparameter lambda t, and if it's ideally infinity, you get almost zero mass under all the graphs with cycles. But in practice, we annihilate to a very high value.
Okay.
So I mean, it's not guaranteed to have zero probability. But all the graphs with cycles will have very, very low probability. At least that's how it is framed.
Okay. One last question, or
Yeah, sure.
Oh no, I'm just asking. Does anyone want to ask a final question? But yeah, thank you for your answer.
Yeah.
Okay. Well, again, I hate the fact that we don't clap properly, but thank you very much.